Hello and welcome back to the video series on linear algebra. So in the last video we covered vector spaces and we looked at vector spaces with functions. And in this video I'm going to be going over something called subspaces. I'm going to have to re-record the video on propositions of vector spaces, so that will be up online soon. But this is subspaces. So what is a subspace? Well, the word sounds like a vector space. What it is the word sub is something, usually a smaller set. It's a subset of something. And so if V is a subspace, V is a vector space over a field F, then a subset W of V, we call that, so it's a subset, we call that a subspace if the following holds. So if I just draw a little diagram here, so if this is V here, so this is V, then this little section here, this is W, okay, this is W here. So it's a subset that is also a vector space. And notice here we've now only got three conditions. This is because we don't need to check all the other conditions, because all we need to do is we need to check that essentially this subset is closed. Because if it's a subset, then we already know associativity is going to hold because it's a subset. And we already know that distributivity is going to hold because it's a subset and it's a member of the bigger space. So if all our operations we do are contained in this little bubble here, this little set here, and everything we do is contained in here, then it's a subset that is also a vector space. So we need to check that as those conditions. So firstly, we need the zero element, the identity, the zero vector, to be in W. So in somewhere in here, we need a zero vector. Okay. We also need it to be closed under addition. What that means is if you take any two elements in here and you add them, they also need to be an element in here. And also any element from the field, we need it to be closed under scalar multiplication, which means if you take any A which is in our field and you take any element which is in W in our subset, AX must also be in W, okay? So it must be contained. So it's going to be closed essentially. And these two properties here mean that our show that if these hold for any of these elements here, any A and F and any X and Y and W, then that means we have a subspace, okay? And that subspace is a vector space. So yeah, so that's what we'll be checking in the following examples. So our proposition here just confirms that our subspace, if it holds, is a vector space, if it holds the above conditions. So the little proof here, which is only it's not really a proof, it's just a quick, simple note that, so firstly, if it holds under those three properties above, we know that it's associative because our set is a subset. Okay, so it's a member of that set. So a fortiori, it has to be associative. Secondly, under addition analysis, we know it's commutative because also it's a subset, so it has to be commutative because otherwise, if it wasn't commutative, it would break the rule and we would no longer have a vector space over the superset, the bigger set. And thirdly, it's got to follow the four axioms, and I've called them definition 2.4, but that's really just a standard definition of a vector space. So it has to be distributive over both scalars and vectors. It has to have the fact that associativity is just a standard over two scalar multiples and a vector, and it also needs to have that the identity, so 1 times x is equal to x. Okay, so some examples of subspaces are So we have subspaces of Rn. We have the null space, which if you've done linear algebra in the past, you'll know what the null space is. You have the column space, and these are of n by n matrices. Secondly, you have the set of all convergent sequences. These are subspaces. Previously we looked at the set of infinite sequences as vector spaces, so the set of all convergent sequences are subspaces. And thirdly, we have the special example, where if we have A, which is a matrix with real entries, with columns and rows L by M, so it's L by M matrix with real entries, then the set W, which is the set of all matrices B in the sort of size n by n, order n by n with real entries, such that A times B is equal to the identity. So it's the identity matrix. It's the identity vector. It's the identity matrix. This is a subspace. Okay. So if you have A, so any matrix A, it's the set of all B such that A times B is equal to the identity. That is a subspace, and we'll prove that one now. Proof. Here's the proof. So firstly, we need to prove, if we go up to here, that the zero vector is in W. We need to prove that the zero vector is in W. Okay, so how do we prove this? So we take any A, which is in, so we say let A be a matrix, an L by M matrix with real entries. We need to prove that the zero vector is in this. Well, this is not that hard, because we see if we take A, just note, so observe that A times, oh, by the way, I made a little error. This is not the identity matrix. I'm used to this being the identity matrix, but because if you take group theory or any other abstract algebra, you'll use this zero as the identity for a set, but this is the zero matrix, not the identity, it's the zero matrix. So if you take A, any matrix A, and you multiply it by the zero matrix, you get, and obviously it's a vector because it's a member of our vector space now. Okay, so we call members of our vector spaces, so members of a vector space are called vectors. And remember, these are not just column vectors or row vectors, these are more abstract vectors. They're just elements of a vector space now. So note, if we take any matrix and we multiply it by the zero matrix, we get the zero matrix again. This is because our vector space is a field. Our vector space over a field, we have we've previously proved that when you multiply any element by the zero element, you get the zero element back, and we've previously proven this. Okay, and so also it's a standard fact of matrix multiplication that when you multiply anything by the zero matrix, you get the zero matrix. And of course, this is a vector because it's a member of a vector space. So we've proved this. So the zero matrix is in this set because when you multiply it by A, you get the zero matrix. Okay. Secondly, we need to prove that it's closed under addition, and this is also quite straightforward to prove. So if we have B, which is a member of W, that if we have, in fact, let B and C be matrices which are members of W, this means that A times B is equal to A times C, which equals the zero matrix. Now we have to prove it's closed under addition. So how do we do this? Well, so what is B plus C? Well, B plus C, let's just take a look at B plus C. Well, if it's closed under addition, that means our element B plus C is also in W. And how do we check an element is in W? Well, to check an element is in W, we have to have that A times that element, so now B plus C, must equal the zero matrix, or the zero element. So does this equal the zero element? Well, let's just try and work backwards then. So we know, so this is how you do proofs in maths. You want to show a result so you can work backwards. So the formal proof would be like this. So we'll start up from here. So let B and C be in W. Then this follows. This implies that A times B plus A times C is equal to 0. But then it follows, this implies that because of matrix by matrix rules, we can use distributivity of matrix rules to take these out. Okay, you can factor out the A here, and this is equal to 0. But this holds for any A. Okay, this holds for any A. And so since it holds for any A, then our element B plus C satisfies this set, the rule of this set, that A times our new element B plus C is equal to 0. Therefore, B plus C is a member of W, so it's closed under addition. Finally, if we let B be an element of W, and we let A be an element of F, which is the real numbers, because it's the matrix over the real numbers, then we know that A times B is equal to 0. But 0, the zero matrix times any scalar is also 0, because the zero matrix is the matrix which is formed of just zeros in every position. So if you multiply this by any scalar A, then you just get A times 0 in every entry, and that's just 0. So we know this is the same as, this is also equal to, so I'll do it down here. So A times B is equal to 0, which is also equal to A times 0, which is also equal to A times B. Okay, and now, because we have this entry here, then we can say this is the same as having so if we started off with, well, in matrix multiplication, the standard rule of matrices is that scalars, when you use matrix algebra, scalars can commute. Okay, so this is the same as having A times B. Okay, hence this implies that A times B is an element of W, so it's closed under scalar multiplication. Now, if you're not quite convinced of my arguments here, where I've just commuted A and B, and up here I've distributed, well, these are standard rules of matrix multiplication. You can prove them, they are essentially defined as that in matrix multiplication, and you can prove these more rigorously, but you would have to use the definition of matrix multiplication. So a quick simple proof of say this commutativity here would be that you have to take matrices, so you'd have to say A is a matrix with entries say I, j, and B is a matrix which has entries j, k. Then you would have to say AB is equal to, it would have to be a sum of Aij, Bj, k, because that's what AB is, that's what the entries of AB is, okay? And of course these have entries ik. Alright, and so then you know by this definition that you could add in a scalar, and you know by the definition of sums that sums are linear. Anyway, so in the next video we'll continue with these properties. Thank you.